Hello, welcome to another module in this massive open online course. So, we are looking at the building blocks and the various fundamental definitions required to develop the optimization techniques, and we have previously looked at the definition notion of a convex set, the convex combination of a set of points, and also the concept of a convex hull. So, let us continue this discussion by looking at something slightly different today, that is the definition of an affine set. So, what we want to look at is the notion, or we want to learn the concept of an affine set, and this is very simple. The affine set, in the previous module we have seen the notion of a convex set. Now, what an affine set is, that is, if you consider any 2 points x1 bar and x2 bar. Okay. So, similar to the definition of convex set, consider two n dimensional points x1 bar comma x2 bar, okay, and now perform the combination theta x1 bar plus 1 minus theta x2 bar, but theta can take any real value, theta can take any, remember in the convex, for a convex combination we had restricted theta to lie between 0 and 1. However, in this case there is no such restriction and theta can take any real value, okay, and this is an important point. Observe there is no restriction on theta. In fact, theta can take any real value, okay, and such a combination. Now, this is an affine combination, and basically you can see that for various values of theta, this represents the entire line through x1 bar comma x2 bar. So, previously when 0 is less than equal to theta is less than equal to 1, it simply represented the line segment between x1 bar and x2 bar. Now, if you remove that restriction on theta, it represents the entire line, that is, any point on the line is captured by this combination theta times x1 bar plus 1 minus theta times x2 bar. Now, if this belongs to the set S, whenever x1 bar and x2 bar belong to the set S, that is the entire line, alright, entire line joining the points x1 bar and x2 bar belongs to the set S. For any 2 points x1 bar x2 bar belonging to the set S, such a set is known as an affine set, that is set S tilde is affine if x1 bar comma x2 bar belongs to S tilde, okay. Remember we've seen this symbol, belongs to S tilde implies theta times x1 bar plus 1 minus theta times x2 bar also belongs to x tilde for all real values of theta, that is, for any real value of theta, that is, for any 2 points given any 2 points in S tilde, entire line joining the 2 points, entire line joining the 2 points the entire line joining the 2 points lies in S tilde. Okay. And note that the affine set is convex, and that you can note, this is an interesting property. Every affine set is convex, correct. The reason is very simple, because if it contains the entire line joining the 2 points, naturally it contains the line segment, that is for any x1 bar x2 bar belonging to S tilde. Since it contains the entire line, or if it is affine, it naturally also contains the line segment, alright. So the convex set is a special case of an affine set, alright. So every affine set is also a convex. I am sorry, affine set is a special case of a convex set, alright. So every affine set is a convex set, but note that every convex set need not be an affine set, alright. Note that also, but all convex sets are not affine. All convex sets are not affine, and that is very easy to see. Take a simple example. For instance, if you consider a circle, correct, which we saw yesterday, is a convex set, because if you take any 2 points, correct, the line segment joining the 2 points is contained, but if you extend that to form the line, you can see that the entire line, so the line segment is contained. So this is your S, line segment is contained in S, these are your points x1 bar, x2 bar. The line segment belongs to the S, but the line does not belong to S, that is, it does not, the entire line does not belong to S. Okay, it's a very simple thing. Okay, so every affine set is convex, but every convex set is not affine. Okay, so these are the this is the interesting relation between affine sets and convex sets. Okay, all right. Now let us look at some examples to understand this better. Examples. Examples of convex sets and affine. Let us look at some examples of convex and affine sets and consider a simple line. For a simple example, for instance, consider a simple line in 2 dimensions. The line, let us say, is given by the equation 2x1 plus 3x2 equal to 6. Okay. Now if you plot that line, it looks something like this. For x1 equals, for x2 equals 0, x1 equals, you can see this is 3, and when x1 equal to 0, x2 equals 2. So if you plot the line, that will look something like, it will look something like this. Okay. So this is the line 2x1 plus 3x2 equal to 6. And remember, line is a trivial example of an affine set, correct, because if you take any 2 points on the line, alright, if you treat the line as a set, if you take any 2 points on the line and join the line, correct, naturally the entire line which is the same line, belongs to that set, alright. So, the line is a trivial example. So, any line is a trivial example of an affine set, okay. So, let us note that. So, this line is affine, line is affine, and it is also convex, okay, because every affine set is convex. The line is also convex. Now, the interesting thing occurs when you look at these regions. Now, the line is partitioning this plane into two regions, if you look at this, okay. Now, this region is the region 2x1 plus 3x2 greater than or equal to 6, and this region is the region 2x1 plus 3x2 is less than or equal to 6, and these regions are known as half spaces. So, the line divides the plane into two regions, 2x1 plus 3x2 greater than or equal to 6, or 2x1 plus 3x2 less than or equal to 6, and these are known as half spaces. These are known as half spaces, okay. Okay. So, you have a line and the line divides the plane into two regions. So, the line is convex and also affine in fact, and it divides the plane into two regions. These are half spaces, and note that half spaces are only convex, they are not affine, okay. So, these half spaces, these are convex and these are not affine. So, a line is affine, which implies it is also convex, but a half space is only convex and not affine. Now, if you generalize this to n dimensions, in n dimensions, one can consider an n dimensional equation which is of the form a1 x1 plus a2 x2 plus an xn equals b, okay, which implies, if I write it in vector notation that we are familiar with, a1 I can write it as the row vector a1 times the column vector x1 x2 xn equals b, which implies, now I can denote this by a bar transpose and this by x bar, this I can denote by x bar. So, I can write this as a bar transpose x bar equals b, okay. And this equation in n dimensions, this represents what is known as a hyperplane, okay. In n dimensions, this is a hyperplane. Which is, in fact, you can see it is affine, okay. So, a bar transpose x bar equals b, this is a hyperplane, a general equation for a hyperplane. This is an equation for a hyperplane, and you can see that this is affine, a hyperplane is affine, which also implies that this is convex as well, right. For instance, if x1 bar comma x2 bar belong to this set S, that is, you can quickly verify this, that is a bar transpose x1 bar equals b A bar transpose x2 bar equals B. This now consider theta times x1 bar plus 1 minus theta times x2 bar, theta times x1 bar plus 1 minus theta times x2 bar. This equals theta times A bar transpose x1 bar plus 1 minus theta times A bar transpose x2 bar, which is theta times B plus 1 minus theta times B, that is equal to B. Okay. Note that there is no restriction on theta, valid for any theta element on R, implies this is affine. If it is only valid for 0 less than equal to theta less than equal to 1, it is convex. In this case there is no restriction on theta, so this is affine. So you can see that a hyperplane is an affine set. Now this hyperplane divides the space into two, the n-dimensional space into two regions, A bar transpose x bar greater than or equal to B, A bar transpose x bar less than or equal to B. These two regions are known as half spaces. Okay. So the hyperplane divides it into two regions, correct. A bar transpose x bar less than or equal to B, these are half spaces that are in fact the general equation of half space you can always remember represented by A bar transpose x bar less than or equal to B. For instance, example, you have 2x1 plus 3x2 less than or equal to 6. You also have the other half space, that is 2x1 plus 3x2 greater than or equal to 6, which basically implies minus 2x1 minus, you take the negative, minus 2x1 minus 3x2 x2 less than or equal to 6. So the general equation of a half space, which is of the form again A bar transpose x bar less than or equal to B. Okay. So the general equation of a half space, so A bar transpose x bar less than or equal to B is the general expression for general representation of a half space. Okay. Thus these half planes, these hyperplanes and half spaces are complex. Therefore the important thing to realize here, therefore hyperplanes and half spaces hyperplanes are affine as well, but for our purposes it is enough to note that hyperplanes as well as half spaces are convex. Okay. Hyperplanes as well as half spaces are convex. Okay. Now what we want to do is we want to explore a practical application, because remember we want to also explore practical, right, applications of the concepts that we learn for optimization. Let us look at the practical application. Let us look at one of the practical applications of the concept that we have just learned regarding convexity and how these influence practical optimization problems that arise in wireless communication scenarios. Okay. So what we want to look at is we want to look at a practical aspect practical application. So for instance, consider a wireless system with multiple users. So what we want to do is we want to start by considering a wireless system with multiple users. Consider a wireless system with multiple users, and for instance, let us say you have a base station, correct? And you are transmitting signals to multiple users. This is, let us say, user 1, you have another, let us say, user 2 somewhere, and so on and so forth. At some other point you have user k. Okay, we are considering a downlink scenario where the base station is transmitting to different users. Okay. Now let P1 denote the power to user 1, P2 denote the power to user 2, so on so forth, Pk denote the power to user k. Okay. So we have P1 Pi equals power of signal, power allocated, you can say power allocated to Pi is the power allocated to user I by the base station, Pi is the power allocated by user I to the base station. Then now we need that, so P1, P2, Pk are the powers that are allocated to the different users 1 to k, but this total power allocated to the different users has to be less than or equal to, correct, the sum total of the powers of the different users has to be less than or equal to the total power, the maximum power of the base station available at the base station. Alright, so that is a constraint that we have in a practical wireless scenario. So the power that is allocated to the different users, that is P1, P2, Pk, these are the powers allocated to different users. These are the powers that are allocated to different users. Now when we consider P1 plus P2 plus Pk, this has to be less than or equal to P, alright. So the sum power of all the users, sum of powers of all users has to be less than or equal to P, which is the total power of the base station. So that has the total base station power. So the sum of the powers of all the users, or basically if you look at sigma Pi, summation Pi I equal to 1 to k, that has to be less than or equal to P. And you can see this constraint is basically P1 plus P2 plus Pk less than or equal to P. This is nothing but a half space constraint, because it is a linear combination of P1 plus P2 plus Pk, alright. Alright, and you can consider the weighting coefficients A1, A2, Ek to be unity, that is 1, and therefore we have P1 plus P2 plus up to Pk less than or equal to P. This in fact represents a half space. Okay. So this is a very important constraint in wireless communication. This is nothing but a half space. So basically the set of all feasible powers, possible powers that satisfy this constraint lie in a half space. That is the interesting interpretation that is that one can make here, alright. So the set of all feasible powers in the wireless scenario, this is an important notion, set of all feasible, feasible in the sense that satisfy the constraint, set of all feasible powers lie in a half space. the set of all feasible powers lie in a half space. Now, you can also have an equality power constraint, that is, you do not want to waste any power and you want to set the power of all the users equal to P, that is P1 plus P2 plus Pk equal to P, and this is an equality power constraint, that is you are replacing the less than equal to by equal to. So, this is a equality this is an equality power constraint, and note that this represents a hyperplane. So, all the feasible powers lie on a hyperplane, represents a k dimensional this represents a k dimensional hyperplane. Okay. All right. So, we have this power constraint in a wireless communication system that can either, if you have an inequality, that is a sum total of the powers of the different users is less than or equal to P, that is the total power of the base station, that is basically a half space constraint, and when you have an equality power constraint, that is sum total of powers of all the users has to be equal to the power of the base station, that basically represents a hyperplane, which means the set of all feasible powers corresponds to a hyperplane in k dimensional space. All right. So, this is an interesting practical perspective to the theoretical concepts of convex sets and affine sets that we have just seen, and we will explore several more links between the various theoretical concepts or the theoretical building blocks of optimization and its relation to practical applications in several fields such as wireless communications, be it signal processing or so on. So, we will stop here and continue in the subsequent modules. Thank you very much.